Welcome back to the second part of this video on 3.06 forces and 2D forces in equilibrium. In the first part of the video, we looked at how to break your forces into components and use them in your F-net equations. But we've dealt with acceleration cases. But what happens if there is no acceleration? How does the case change, and what kind of special situations do we have then? So, without further ado, let's progress and get this done. So, we are dealing with no acceleration. And with no acceleration cases, and specifically, we can talk about objects that are at rest. When we talk about objects that are at rest, we need to make a few assumptions. We have to make a few assumptions that have to do with the equilibrium of an object. What does equilibrium mean? It kind of think about balance. There has to be a balance of forces. Now, there are many different kinds of ways in which an object is balanced. We have, number one, translational equilibrium. This, imagine the object being able to move left, right, up and down, etc. The object is not moving in that direction in any way. Number two is your object cannot spin around. They cannot rotate. They can be on the spot and rotating, but if they are not at rest, okay? They cannot experience forces that cause them to rotate on the spot either. The last kind of equilibrium, which you may or may not see this year, actually a little bit, but it's not going to be talked about in that much detail, but vibrational equilibrium. So that just means something kind of goes back and forth, and something that vibrates. And here I kind of made something very quick that I can kind of show you what that looks like. I know, haha, Darth Vader. So translational motion is, imagine you have someone moving from one spot to another spot. So direct motion, no rotation, nothing like that. Translational motion. Rotational motion is having to do with an object spinning on a spot like this. Darth Vader spinning, that looks pretty nice. And last but not least, vibrational motion. Imagine you took this object and you kind of shook it back and forth in a way, or it does it by itself. That's vibrational motion. Now, when we talk about absolute equilibrium, the object is not doing any of those. For us, we will simply deal with translational equilibrium. We'll just look at that. We will assume everything else is not rotating, vibrating, etc. We're looking at the conditions for which an object is not moving side to side or accelerating side to side, up and down, etc. In those cases, the sum of all forces equals to 0. And since we are only looking at a 2D plane or looking at 2D cases, we will look at two axes in which the sum of the forces in the y direction equals 0, and then the sum of the forces in the y direction equals to 0 as well. Here is a little shorthand I can show you. So if you think about this way, if you take a look at the x direction, and I'm going to assume this is left and right. Oh my god, I totally assume that the x direction is the left and the right. You can kind of think of it this way. Because the forces should sum up to 0, the forces pointing right should equal all the forces pointing left. So in a way, you think of it this way, for forces, or force components actually, force components left, or just forces in general, equals force components right. Okay? They should be equal. Okay? There's a balance. And same thing with the y. Let's say y is up and down. And I'm just choosing these axes arbitrarily, but left and right could very well be into the page, out of the page. Up and down could be, I don't know, this could be forward or backwards. depending on which plane you're talking about. But just in that axis, the forces going one direction must equal the forces pointing in the opposite direction. So in my case here, I would say that the forces pointing up should equal all the forces pointing down. And these all include components, okay? So the reason why you can do this is stemming from the fact that F net is equal to 0. If F net is equal to 0, then all the forces that are opposing each other are equal after you rearrange the equation, okay? So instead of me writing F net equals 0, blah, 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 I'm just going to use this format for my questions, okay? It actually makes things a lot easier in some ways, and it kind of makes a little bit of intuitive sense. Now, I've talked about how we dealt with acceleration being 0. There's actually two situations where that could happen. One of them is if an object is moving a constant motion. The other one is, well, in that case, the object must be moving a constant velocity. The other one is the object at rest. In both cases, acceleration is 0. But if something is moving at constant velocity, we call this dynamic equilibrium. Dynamic equilibrium, meaning something is dynamic, it's still moving, it's still in motion, but all the forces balance. On the other hand, when an object's at rest, it is not moving, it is static. We call this static equilibrium. But regardless of the case, whether which one we talk about, acceleration is still 0, and the net external force acting on an object is still 0, which means F net is 0. Okay? So here are just some words that you may or may not see. In fact, you'll see static and dynamic later in chemistry next year when you guys talk about equilibria. Ooh, fun stuff. Anyways, the idea will come back. It's just a nice term to kind of familiarize yourself with. Let's take a look at one example because we love short videos, don't we? Let's take a look at a sign. A sign is suspended using ropes as shown below in the diagram. And you know how Levi loves his tea shop, so Levi's tea shop. Haha. Love it. Okay. Levi's tea shop. This is a sign piece is suspended, and Levi would probably never suspend a sign with some weird angles involved. But anyhow, let's say he did. If tension 1 is 110 newtons, that's the question, what is the weight of the sign? And when we say weight of the sign, don't forget the weight is not the mass, it is the force due to gravity, okay? We want to find the Fg. This is what we don't know about the sign. So below I kind of wrote down some steps and some follow-throughs, but anyhow, let's talk about what happens when we draw a free body diagram when something's in equilibrium. You might be thinking, oh, look, I'm going to draw a free body diagram on this sign over here. But it may or may not help you. And let's take a look at why. Because right now you have Levi's shop. Let's say you draw the free body diagram. There's Fg. Right? And then you got a rope, which then means it must have to do with something to do with tension. And because this is not the same rope as this rope or that rope, it is tied here in the middle, I'm going to call this T3. Now, we don't know what T3 is, do we? And there's no way to find it because we have no relationship between T1, which is something we do know, T2 and T3. We have no idea what it is. But then we do know that in this case, T3 must equal to Fg since the sign is not accelerating. The up forces equals the down forces. That's useful information, but that probably is not a good place to begin the analysis of your problem. It's a good start. What would actually be more useful is probably looking at the equilibrium at this point here. Yes, you just heard me. You can draw a free body diagram on any arbitrary point that you want. It doesn't have to be an object. It can be on any point you want. And of course, you want to choose that point strategically to help you figure out the question. And in our case, it will make the most sense if we chose that point to be where all the forces are connected, are interacting at the middle. So over here, I've drawn a simplified diagram, and this part of this is cut off. So you have this force over here, which is T2. You have this force over here. I don't know why I'm redrawing the arrows. You have this force here, which is T1. And the force that's pulling all of this down, yes, it is T3, but since T3 is equal to Fg, I wrote Fg instead. This is just equal to the Fg of the sine Levi's T-shop. So that's going to be our free body diagram. Number 2 is done. Check, check. 3 is determine the x and y coordinates of your system. So I'm going to choose these ones here because it's generally helpful. It's easier to work with because look at the angles. They already give us the angles in relation to the horizontal, which is useful. So I've done my x and y coordinates. So then I can go to 4, which is break your forces into x and y components. All right, so let's break these forces down into their x and y components. We have this one, which is T2x. We have this one, which is T1x. Fg is just vertical. We don't have to break it into any components there, but we have here T2y. And then we have this one here, which is T1y. And actually, we could do this. We can even write this in terms of cosine and sine. And in fact, let's make this a little easier because I drew the triangles over here. So 25 degrees, which makes this the similar triangle. Or if you want to do it the other way, since it's 25, this one over here must be 65. The right triangle here must make this one 25 degrees. And then same thing with this one being 55 degrees. Of course, if you use the Z rule, geometry, you can reason out that this is a similar triangle, similar side as well. Okay, there. There are your angles, which makes your T2y equal to your T2. And this is the opposite end, which is sine of 25 degrees. For T2x, on the contrary, will be T2. And instead of sine, it is the adjacent side, making it cosine of 25. The other side is very similar. This will be T1 cosine of 55. And then T1x, this will be T1 sine of 55. Okay, so I've broken down all of my vectors into their components. 4 is a check. And now, this is specific to your equilibrium problems. But in fact, in a generic problem, you also do want to ask yourself, is your object accelerating in any of your axes? And because we know this thing is in equilibrium, we can reason that in the x direction, the acceleration is 0 meters per second. In the vertical direction, the acceleration is also 0 meters per second squared. Meters per second squared. The reason why we want to determine this before we start the problem is because we need to know how we write our F net equation. If we don't know the acceleration is 0, there's no way to say that, what's our F net equal to? And if we know if it's 0, it makes our life a lot easier, which means we can use these. Or in my case, I'm going to use these guys over here. Okay, but now we know that, we can now write my F net equations because I know the sum of our forces are equal to 0. So let's do this one. All right, I'm going to actually write out all of the equations out for x and y. So I'm going to do it down here, might get a little packed. Along the x direction, I have my x component forces. My T1x equals my T2x. Also meaning that T1 cosine of 55 equals T2 cosine of 25. Okay, so that is the first thing. The second thing is along my y direction. I'm going to leave some space above because I'm going to probably use that component later. In the y direction, all my up forces equals my down forces. Up forces include T2y and T1y. Both of these are upward forces. This equals my downward force, and the only one I have is FG, the one that we need to solve for. And if I want to write this out even more, I can write this is T2, actually it doesn't matter the order, T2 sine 25 plus T1 sine 55 equals to FG. Okay. Now, we have 25. We have 55. We have T1 actually because it's given here in our question. Let's just write it down. 120, I think. No, 110. We do have this. But we don't have T2. That's a problem. In order to get T2, we will have to see if another equation contains T2. And voila, there it is. T2 here. But can we solve it? Well, we have 25 with 55. And T1 we do have. So we can solve for T2, but using our x component forces. So let's do that. Let's solve for T2, okay? Rearranging everything, which means I'm going to divide both sides by cosine 25, which gives me T2 is equal to T1 cos 55 over cos of 25. And like I said before, I am going to do all of my calculations at the last step. So bear with me. We have some algebra coming our way. And like I said, it is very useful to use algebra. Don't put in the numbers first, because it not only saves you from making silly mistakes on your calculator, it saves you from rounding your values mid-question and not getting the right answer at the end. And number 3, it helps you to really see what kind of components or characteristics, forces, vectors, scalars are coming into play in your question. When you make a mistake, it's easy to spot why from a conceptual perspective. And it's also easier for me to see where you've made the mistake instead of seeing a bunch of numbers which I have no idea where you get it from. So it is a good skill to solve all your problems algebraically, okay? So what I'm going to do next is I'm going to substitute the T2 into this equation. I'm going to have a lot of variables, and don't be afraid of variables, because a lot of people are, and I was that person too, and it's okay. But you got to conquer your fear of your variables. Otherwise, life will not get easier in the long run. And again, we do all this for the long run, right? So here I'm just solving this and substituting everything in. Now substitute everything carefully. Don't miss anything. And all of this should give us your FG in the end. Okay? So let's put in all our values. T1 was 110. This is cosine of 55 over cosine of 25 times sine of 25, I'm running out of space, plus 110 times sine of 55. If you've done all of these calculations correctly, and I get 119.5 which rounds up to 120 newtons, being the weight of Levi's T-sharp sign. So let's look at some of the takeaways from doing this problem. Now, you always want to, again, free body diagram, super important. Some of the new things we've introduced. First things first, choosing the axes. Choosing the axes in a way that makes your life a lot easier. And why you want to choose your axes? Because it helps you break your forces down into the components relative to those axes. From that point onwards, you can then say, well, is my object accelerating along that axis and the other axes? If it isn't, you have an equilibrium case, a translational equilibrium case, which you can apply the sum of all forces equal to 0. And when you do that, the shorthand is saying that the forces in one direction equals the forces in the other direction along that axis, instead of writing your whole F-net equation down. And because you have two equations, you have two tools to use to solve for unknowns, which means in any given question, you should have two unknowns and still be able to solve it, because you can substitute and solve it from the second equation. Okay, so here are those are some takeaways when you deal with 2D forces in equilibrium. Some of these are translatable into non-equilibrium cases as well, but here is a start. So hopefully you got something out of this video, and I hope you enjoyed the series of 3.06 on 2D forces in equilibrium. Thank you for watching. Stay tuned. We will talk about inclines next when we deal with a different set of axes. Good luck, and see you next time.